Let's recall that the topologist sine curve is the subspace T of R2, defined by, well, it's the union of two sets. And the first set, denoted A in my picture here, is the graph of the function sine 1 over x, for x from 0 to 1, not including 0. And we're taking the union of that with this vertical interval b on the y-axis for y from negative 1 to 1. All right. And in exercise 6.42, we get to prove that the topologist sine curve is connected but not path connected. Now you remember that a path connected space does have to be connected, but the converse is not true, as is evidenced by this example. So first let's prove that T is connected. This is the easy part. Well, first of all, the set A here is certainly connected because it's the image of the connected interval from 0 to 1 under the continuous function f from R to R2 given by f of x equals x sine 1 over x. Okay. This is basically a parameterization of this curve in R2. And all right, so A is connected. And we know by exercise 2.21 a good while ago that closure of A is the entire entire topology sine curve T. In other words, everything in B is a limit point of A. And theorem 6.8 in this chapter tells us that if a set is connected, then its closure is connected too. So we know that T is connected. That takes care of the first part, and now let's try to show that T is not path connected. We're going to proceed by contradiction. So suppose for contradiction that we have a path that begins somewhere in B and ends somewhere in A. And I've chosen 0, 0 as a point in B and 1 over pi 0 as a point in A, although those particular choices don't really matter. And all right, well, I want to focus attention on the set B here. Okay. Notice that that's closed in R2 and therefore also in our curve T. And all right, well, that means that its preimage under P is closed in the domain of P, right? Closed in the interval from 0 to 1. We're going to prove that its preimage is also open. And since that space, that interval from 0 to 1 is connected, if we have a subset that's both closed and open, there's only two possibilities for what it could be. Right? Either it's the empty set or it's the entire space. But neither of those can really happen because, well, we know that because the path begins at the origin, which is in B, 0 is in the preimage of B, and because the path ends at a point in A, in other words, P of 1 is in A, it means P of 1 is not in B, and 1 is not in the preimage of B. Okay. So because of this first statement, the preimage of B is non-empty, and because the second one, it's not equal to the entire interval from 0 to 1, okay, because 1's not in there. So that is the idea of the proof. The only step that requires some more work is showing that the preimage of B is open. Okay. So let's give that a try. So to prove that the preimage of B is open, we're going to fix any real number t in it, and we have to find a neighborhood of that t which is contained in preimage of B. All right. Now if t is in preimage of B, then P of t is in B, as I've illustrated here, and that means that the x-coordinate of P of t is 0, and the y-coordinate is, let's call it y sub t, whatever it is. Okay, now what does it mean intuitively that preimage of B is open? Right? In other words, that we can find the neighborhood of t contained in preimage of B. Well, it's going to mean that there exists some little neighborhood of t such that when you map it by P, you're in B, right? So it means there's some little piece of path through this point P of t, which is entirely contained in B. All right. Now, why do we know that such a thing has to exist? Well, here's the basic idea why. Suppose that part of that path was actually in A, right? Well, then we have a point on the path with a positive x-coordinate. we also have a point on the path with an x-coordinate of 0. And by the intermediate value theorem, we know that there must be points in the path with all of the x-coordinates in between as well. Problem is that to get a bunch of those x-coordinates, we would need to take points on the graph all the way up here. And those points have really big y-coordinates. In particular, they have y-coordinates that are really far away from this y sub t. And well, if we took our little piece of path to be small enough, then there's no way that it's going to reach all the way up to these points up here. Okay? So that's sort of a rough intuitive idea of what the issue is. Let's see if we can make that rigorous. All right. Well, given this this t, such that p of t has y-coordinate y sub t, let's define this interval I to be interval of radius 1 about y sub t. And so I sort of illustrated that here for our particular picture. And I'm going to define another set n by taking r cross that I. So I get this infinite sort of horizontal strip, and then intersecting with the topologist sine curve. Okay? And that just gives me the part of t which is inside of that strip, and in particular below this dashed line. All right. Now I claim that's a neighborhood of the point p of t in t. Right? Well, it certainly contains p of t, because the y-coordinate of p of t is definitely contained in I, and p of t is certainly in capital T. All right, so it contains the point p of t, and moreover it's open in t because r cross I is open in R2. All right, so since n is a neighborhood of p of t, and we know that p is continuous, we know that the preimage of n is a neighborhood of t. So that is illustrated right down here. And here's our path mapping the interval from 0 to 1 to our topologist sine curve. And I've found this set n whose preimage contains is a neighborhood of t. And all right, well, I've drawn that the preimage of n as having a couple pieces here, right? Since it's open, we know that there exists just an open interval j, which contains t and is contained in preimage of n. Right? And I want to focus attention on that j because I know that j is connected. All right. So, all right, we have an open interval j in preimage of n containing t. We're going to show that this j is contained not just in preimage of n, but actually in preimage of b, okay? which will give us the neighborhood we need. And we're going to do that by demonstrating that the points in p of j are all in b, right? In other words, they all have x-coordinate equal to 0. Okay? So why do the points in p of j all have x-coordinate equal to 0? Well, like I said, this open interval j is connected, and so its image under this continuous function p, and also under the projection p sub x onto the first coordinate, right? The connected set, the image under a continuous function is going to be connected. Okay? Now, what does the composition of these two functions do? Well, p just maps this interval onto the path in t, and then p sub x projects that down to the x-axis. Okay. So, all right. Well, what does this set p sub x of p of j look like? Well, since t is in j, and p of t is a point with x-coordinate of 0, I know that 0 is in that set. Okay. And well, I just said it's connected. Now I'm going to show that its missing points arbitrarily close to 0, and then the conclusion is going to be that, okay, it has to be just 0 then, right? And so from that it'll follow that everything in p of j has an x-coordinate of 0, so it's in b, and so j is in the preimage of b. All right, so why is this thing missing points arbitrarily close to 0? Well, P of j is a subset of n, so the x-coordinates of points in P of j are a subset of the x-coordinates of points in n. And the x-coordinates of points in n are just x values between 0 and 1, such that the point xy is in t for some y in I. Okay, in other words, we're going to take points on t with y coordinates in I, so basically points on the graph below this dashed line, and look at their x coordinates. And I've tried to illustrate that here. You can see that if you take sort of this piece of n and apply a piece of x to it, you get this interval here, and you get another little smaller interval here, and a smaller interval here, and smaller intervals. But they're for this entire set piece of x of n is missing points arbitrarily close to 0, right? Because there are all these points in the graph up here, which are the only points with certain x-coordinates, right? And so those x-coordinates are going to be missing from piece of x of n. And just to be sure, I've written down some of the points that are missing. In particular, if, as in the case of our picture up here, y sub t is less than or equal to 0, then, well, if you plug in these values into sine of 1 over x, you're always going to get 1. So these are x values where the y coordinate is 1, so it's the points at the very top here. And, well, those points are not in n. Okay, so p sub x of n is missing these points in that case. And, well, if y sub t were greater than or equal to 0, then my I would be more like this, and my n would be missing the points on the graph, the points in t down here. And, all right, well, if you plug these values into the function sine 1 over x, you get negative 1 always. And so these x-coordinates would not occur for points in n in that case. All right, so in either case, we've shown that this set is missing points arbitrarily close to 0. So that set has to be just 0, right? Because it contains 0, we said. If it contained anything positive, then it would contain everything between 0 and that positive number, which would contradict what we've shown here. Okay, so that's just 0. And we've found our neighborhood of t in the preimage of B, proving that preimage of B is open. And that completes our proof that t is not path connected.